You go.
Okay, so improper integrals is a topic that a lot of people struggle with in BC. So today we're going to make an improper integral videos. So we're going to start with improper integrals with infinite limits, and if you focus on this graph, this will be the first one that I do. I'm actually going to show you the basics of each graph, and then we'll do examples at the end. So when you look at this graph here, it's basically asking for the integral from a to infinity. So it would be written as the integral from a to infinity of f of x dx. Now, when you do improper integrals, when you do an integral, this is supposed to be a finite number, and you know infinity is not a finite number. So what you can do is you can do the limit as a value. So let's say b goes to infinity from a to b of f of x dx. And by doing this, since it's a limit as b approaches infinity, this will give you this. And so this is the improper integral when a limit is going to infinity of b of a to b of f of x dx. Okay, now when you move it over to this graph, this is actually a very similar graph, except it's coming from infinity, negative infinity. So we're going to do the exact same thing. So the integral from negative infinity to b of f of x dx is how you would write that. But like I said before, this has to be a finite number. So let's make this the limit as a goes to negative infinity of the integral from a to b of f of x dx. And just like on the other side, this is equal to that. Okay, so like I said, I just showed you these two improper integrals with limits going to infinity. But an important note about both of these is if the limit exists, the proper integral converges. Otherwise, it diverges. Okay, this is very important when doing these two improper integrals with infinite limits. Okay, this is the last basic improper integral that we're going to do before we start doing examples. Okay, now as you look at this graph, you can see that it approaches negative infinity, and it also approaches positive infinity. And so in order to do a graph like this, well, you're going to have to split it. So you can pick wherever you want to put a little breaker, you can put one here. So I'm going to put a line here and call it C. And so by doing this, originally it was the integral from negative infinity to infinity of f of x dx, correct? But now since I inserted the c, I can put the integral from negative infinity to c of f of x dx plus the integral from c to infinity of f of x dx. And like I said before, in order to do an integral, both of these have to be finite numbers. So we're going to break this down even more. And like I said, I already labeled this one as b and this one as a. So for the first one, we're going to do the limit as a goes to negative infinity. Let's make that more clear. So the limit as a goes to negative infinity from the integral from a to c of f of x dx. So this one is going to go down to this one. And then when we redo this one, we're gonna make it the limit as b goes to infinity times of the integral from c to b of f of x dx. Okay, so we have values for both of those. So in order to get the total problem that we were doing, we just add them together like they did in these. So the total integral that you would do is the limit as a goes to negative infinity from the integral from a to c of f of x dx plus the limit as b goes to infinity from c to b of f of x dx. And this equation is the answer to the improper integral negative infinity to infinity of f of x dx. Okay, and just like the other ones, it is important to know with this type of improper integral, if both limits exist, the improper integral converges, but if either limit fails to exist, the improper integral diverges.
Go.
Okay, so starting with some of the examples, our first example, we're going to do a problem which is going to be 1 plus e to the negative x. And we're going to use the bounds x of negative 2 and then x to infinity. So I'm going to graph that. And it looks like this. Okay, so I'll draw that as a little picture over here, so you guys can remember what the graph kind of looks like. And this is honestly a very similar graph to the ones on the examples. And so let's just say x equals negative 2 is right about here. In infinity, so like I did in the examples, I'm going to put a b here. Make infinity limit as b. So let's go ahead and write that integral. So the integral from negative 2 to infinity of 1 plus e to the negative x dx becomes the limit as b goes to infinity, integral from negative 2 b 1 plus e to the negative x dx, correct? Okay, well this is addition, so this is actually, the bounds are there, yes, but we're gonna solve the integral as if there's no bounds to start off with. So solve the integral like a regular definite integral. And so the antiderivative of 1 is x, and then the antiderivative of e to the negative x is negative e to the negative x. Put it in brackets and do our bounds. Okay. My bad, that's supposed to be a b. Okay, and let's continue. So we're gonna go ahead and plug in b here. I'm just gonna do a bunch in brackets. And since this has a b in it, then you put the limit as b goes to infinity in front of it. And then you subtract negative 2. Okay, so the limit as b goes to infinity is going to be infinity minus e to the negative infinity is going to equal 0. Okay, so infinity minus 0, and then we're going to minus negative 2 minus e squared. Okay, so this negative is going to distribute and make all those positive, so you have infinity minus 0 plus 2 plus e squared. Okay, well, adding and subtracting any of this from infinity doesn't really matter. It's going to equal infinity. And since that is since that is a definite, it's not a finite number, the integral diverges.
Go.
Okay, so for the last example, we're going to do the function f of x equals 2 over x squared plus 1, and we're going to make the bounds infinity, negative infinity to infinity. Okay, so we're going to go ahead and draw that integral, right? So integral from negative infinity to infinity of 2 over x squared plus 1. Right? And like I said before, well actually, I'm gonna go ahead and graph it. And the graph looks something like this. As you see, it's graphing. So that's actually similar to what we did before. So I'm gonna draw the picture right here so you know what it looks like. Okay. So we're going to set, like I said before, we're going to need to set a value from start, so we'll just basically do a and make that 1. Okay. So 1, sorry. And then we'll make this side a as it goes to negative infinity and this side b as it goes to infinity. So this integral will then become the limit as a goes to negative infinity of the integral from a to 1, 2 over x squared plus 1 dx, plus the limit as b goes to infinity, integral from 1 to b of 2 over x squared plus 1 dx. And now we solve. If it helps, you can solve these separately and then add them together. It really doesn't matter, but for some people, that is how they avoid confusion. Okay, so when solving this one, you can pull the 2 out to the front. And when you do that, so when you pull the 2 out to the front, you have the integral from a to 1 of 1 over x squared plus 1 dx. The limit as a goes to negative infinity. And you look at that, you'll notice that this is going to be the arctan of x anti-derived. So it'll be 2 times the arc tan of x. Leave the 2 on the outside because it's constant from a to 1. And you have to remember to put this limit here to negative infinity. Okay? And then also, remember when you substitute in, you only put the limit as a goes to negative infinity if a is in the problem that you're solving for. So we'll do the limit as a goes to negative infinity of, my bad. It's top minus bottom, correct? So it's going to be 2 times the arctan of 1 minus the limit as a goes to negative infinity of 2 times the arctan of a. Okay, and when arctan goes to negative infinity, it's going to equal negative pi over 2. So it's 2 times the arctan of 1 minus 2 times negative pi over 2. We'll put those in brackets. Which becomes 2 times the arctan of 1 plus pi. Okay, and so now that we have that side solved, let's come over here to this side. Okay? So, like I said, you can pull the 2 out to the front, so the limit as b goes to infinity. 2 times the integral from 1 to b of 1 over x squared plus 1 dx. This is arctan when it's anti-derived. So the limit as b goes to infinity of 2 is constant, can stay on the outside, times the arctan of x from 1 to b. And then you plug it in, and remember, you subtract the bottom from the top. So 2 times the arctan of b minus the limit as b goes to infinity of 2 times the arc. Ooh, my bad. This should be 2 times the arctan of 1. No, of b. Okay, I messed this up. I'm just going to do this step over again. It should be the limit as b goes to infinity of 2 times the arctan of b minus 2 times the arctan of 1. Okay, and the limit as b goes to infinity of arctan is pi over 2, so that will be 2 times pi over 2 minus 2 times the arctan of 1. Okay, and so when you add all these together from the bottom, it'll be 2 times the arctan of 1 plus pi minus 2 times the arctan of 1.
So it's 2 pi. Oh.
Anyway, 2 times the arctan of 1 minus 2 times the arctan of 1, these two cancels, which will give you the total answer, which gives you a total answer of 2 pi. Therefore, the interval converges.
Go.
Okay, these are the last 3 concepts I'm going to show you, and I'm going to do some examples at the end. If you look at these, I'm going to actually kind of rush it, speed it up a little bit, because I know if y'all are anything like me, y'all do not like watching videos. Anyway, these are very similar to the ones that you did before, except instead of them giving you bounds, you actually have a bound. So, like here, it has a vertical asymptote at x equals c, so the integral from a to b of f of x dx is basically the limit as a goes to c of the integral from a to b of f of x dx. And this is an infinite integral because at an asymptote, it begins to get infinite as it never hits the where it has a vertical asymptote at. Okay, and then on this one, same thing. Limit as b goes to c, the integral from a to b of f of x dx.
Can you guys give this to Kayla when she comes back?
One is it's just like the splitting one that we did before. It's the limit as m goes to c from the integral from a to m of f of x dx. And you're going to add the limit as n goes to c of the integral from n to b of f of x dx. And you're looking at me and you're probably wondering, where is she getting n, where is she getting n from? Well, the vertical asymptote is at x equals c, and so like you did before, you're going to have to split them. Okay, you're going to have to split them. So if you do one going to m, you can set m as one and you can set n as the other, and then you can solve the improper integral. And it is important that integrability does not imply continuity.
1, 2.
Okay, so for our third example, we're going to do the integral of 1 over x plus 8. And this is similar to what we have doing, what we've been doing before, except this here is a vertical asymptote. So you know for a fact that one of your bounds is going to be -8. Okay, and so let's just do the integral from -8 to 0. That's just a choice that I picked. And since -8 is a vertical asymptote, you have to make it into a limit as a value. So let's say b goes to -8. And put a b there. And then it's of 1 over x plus 8. And then when you anti-derive that, it's the limit of b goes to negative 8 of the ln of the absolute value of x plus 8. From 0 to b. Oops, from b to 0. And then when you continue, let's go ahead and plug these numbers in. So the ln of, you don't have to put the absolute value because 0 plus 8 is positive anyway. And then subtract the ln of b plus 8. And don't forget to put the limit here, like I did. So the limit of b goes to negative 8, the ln, absolute value of b plus 8. Okay, and so since the b is not negative, this is the typical picture for an ln function. And so basically, from this picture, you know that it's going to go to negative infinity, which therefore makes it divergent.
Go.
Okay, so here's an example of f of x equals 1 over x squared. And so we did it from the integral from negative infinity to infinity. And so what we did before, we picked a value where we could split it, and we picked the value of 1.
3, go.
Okay, so anyway, we did it from negative infinity to infinity. And remember, you have to split it, so we picked a value of 1. So we did the limit as n goes to negative infinity plus the limit as n goes to infinity. And we did it from bounds from n to 1 and 1 to m. And then when you solve it all the way down to the bottom, you get the answer of 0.